Yeah, so talking about roll dynamics, okay. Um, so yeah, in terms of what we covered today, so we've got double wishbone suspension, talk about some different ways that can be arranged to give you different how they affect things like camber and what happens in rebound and compression. Talk a little bit about roll centers, how you determine the roll center, for different suspension types, and then move on to do some stuff about working out what the roll angle of the vehicle would be, the things that influence roll angle, how roll angle is actually calculated for steady-state corners. So first off, double wishbone suspension. It's the predominant system used in motorsport. Okay. One of the big advantages is the fact that the kinematics of the links is very important to handling. Okay. Like I said, the way the lengths of the links and the way they are orientated can make big differences to how the vehicle performs in courses. Okay. Small changes in geometry can make significant changes to wheel movement. I'll talk about that in a moment. That's what we mean by the kinematics. We're actually talking about the motions and how when the wheel goes under compression or rebound, how those links can actually change various aspects of the performance. Okay, and there's across the axle there's two basic movements: bump and rebound. Okay, so that's the up and down. And that's when both wheels move in the same direction at the same time. So obviously that's like body bounce and heave, when the whole vehicle pushes down on both sides or lifts up on both sides. Is where you get bump and rebound, and then obviously the other type of movement is roll, okay, where the wheels move in the same in the opposite direction. So as the body moves, okay, the motion between the body and the wheels. Obviously, that the wheels are going to go in the direction. One side will extend and the other side will compress. Now, obviously, the way that looks in pictorially is you get a situation like this. So we've got here double wishbone suspension looking at the rear, okay, in front. Okay, A is just the equilibrium position, not moving in left. Okay, you can see B, the body is moved down, but the wheels have moved up. Okay, you get this. This is the way these links have been arranged. As the body moves down, the wheels actually can slightly inwards. Then conversely, in option C, the body is moved up and the wheels move down. You can see that when the body is raised up, the wheels come slightly outwards. Okay, and then here we've got up to D, the body is rolling because of the way that the suspension is set up. We've got the wheels also rolling. That's just a generic setup, but we can have a look at some specific layouts and the impact that has in these different situations. So the first one is also known as parallel length, equal length wishbones. Okay, so this one, the wishbones themselves are equal in length and they are parallel to each other. In fact, this the chassis setup very good. So yeah, so this is parallel. So obviously, basically the whole thing set is sets up like a parallel. Okay. So as the vehicle moves up and down, rebound and so which is the second image there, you can see that the wheels also move straight up and down. There's no camber at all. But obviously, conversely, as the vehicle rolls by 4 degrees there, okay, you can see that because they're equal length and they are parallel, the amount of body rolls, in this case 4 degrees, the wheels will also camber by 4 degrees because you've got a simple parallel. So you've got no camber recovery. No, that's cool. Okay, there's no camber recovery. No camber change involved, but there's zero camber recovery involved. Okay? And the reason why we call that camber recovery is that, like I said, obviously you've got, imagine the vehicle is rolling to the right, that means it's going round a left-hand corner. Okay, and ideally you want the wheels to be cambered towards the centre of the corner. You can see quite clearly that the way this is resulting is that the wheels are cambered outside. You can see the load being applied to the wheels, denoted by the arrows. Okay, it's going around the left-hand corner, all the loads are going to be on this side. Okay, and ideally you want the camber to be cambered towards the inside of the wheel, because then you get that additional camber thrust effect, additional natural load. Because there's no, because they're parallel and equal length, the whole thing then roll out to the same volume. But in squat or dive, there's no change in camber, which is what we've designed. The next type is where you've got so to solve this camber problem, okay, there are some options. One obviously is to stiffen everything up, okay, and give it additional roll stiffness to stop it from rolling in the first place. That's obviously one way, but obviously that's not always suitable because you don't necessarily want to have super stiff springs. Certainly in terms of ride comfort and traction and various things like that, so that's possibly not ideal. You can obviously add some static camber to the wheel camber, we'll see what that does, okay? Or there's another way you can do it, is use converging instead of instead of parallel wishbones, and the other one is to use a short long arm wishbone. So, obviously converging is where you've got two wishbones that are not parallel to each other. So instead of the big parallel to each other, that you have the converging. And then this is short. So if we go to the next one. So this is converging. Okay, so those two planes are now not parallel to each other. You can see that what happens with this under bump, there is some camber being induced, okay? So that we get a bit of scrub on the wheels, and we get a bit. So under squat and dive, the wheels are actually camber. Okay? But you can see with roll, when the body rolls by 4 degrees, the wheels only have a change of about 2 degrees. It depends on which wheel you're looking at. Okay, so you've got 50% camber. So the wheels. The body rolls by 4, the wheels roll out by 2, 3. You can see that the left wheel is negative because that's the wheel is relative to the car, it's negative camber. It's adverse camber with respect to the corner. And obviously the right rolls out of it. It's what and dive when the body moves up and down, you get a change in camber of the wheels. Okay, and the other type is unequal length wishbones. So that's the situation we've got here, often the top wishbone, we've sorted the bottom wishbone, okay? They could be parallel or they could be converging, and as it moves up and down, you get a change in camber as well. Okay, so you can also alter the camber recovery. So you can see that with the 4 degree roll, we've got plus 1.9 on the right, minus 2.4 on the left, okay? And then also in bump up and down, you get scrub under the camber. So we often try and optimise the performance in the corner, not along the straight. So if you look at the Formula car, yeah, that's going to have this sort of.
Is that compared to just a strap?
Sorry? Yeah, I'll talk about how that moves. With a strut, obviously, the motion of the top, where the wishbone connects to the top of the hub, okay, with the strut, that moves in a 90 degrees with respect to that point. Okay, yeah, basically you've got a phase setup. Okay, so yeah. In this example, little change, okay, so very similar to the unequal length, to the converging thing, but slightly more camber recovery. And the real advantage of the unequal length comes with short wishbones. Okay, so obviously these are quite long wishbones, with the body being very narrow. Okay, that's benefit. So when you put a virtual where you've got as much space with these sorts of wishbones, that's quite a significant change. So, with case studies, this is an old F1 car now. They don't look like that anymore, but well, it does show. If you look at the wishbones, you've got the wishbones here coming out of the car. Okay, so it's very similar to, but like I said, it's basically got a parallel setup, so obviously. And well, what you do know is that there's a lot of static camber and negative camber. 4 degrees on both sides. Okay? But when you roll, obviously, if you roll by 2 degrees, obviously -4, and you get an additional 2, so you get -6. On this side, because you've got -4, you add 2 to that, you get -2. So you've still got camber operating in the right direction for the outside wheel. Because of that static. So you can deal with the adverse camber by giving it static camber. And obviously, from the one car, you can see that. The one car going down straight with actually. Now, if you look at Formula 3, which is one of the another case. Oh, sorry. There's your F1 car under roll camber. So this is Formula 3. Okay, so there's Formula 3. One of the ways that Formula 3 have had it before in the past with the teams is they actually join the lower wishbone together at the same point. So the upper wishbones are shorter. Okay, so you've got shorter. They're also not necessarily parallel. You can see they've given static camber. They can camber on both sides. Okay, with 2 degrees of roll, this is dropped to 0.3, no, -0.3, this is -0.6. You see we've still got some negative camber on both sides. So with the outside wheel, we're still in the sort of way, you've got a bit of there's a bit of camber recovery as well.